this sp hybrid orbital, s character will be 25. In the sp3 hybridization, p will be 75%. A is triple bond is there, that's why sp. B here once again sp because two sides double bond is present, and C is sp2 will form. To represent an organic molecule in a three-dimensionally, following convention should be kept in mind. Hello everyone, this is Harshita Bhavasar from Vidhyaashram Temple of Excellence. Today we are going to start up with a new chapter, that is Organic Chemistry, some basic principles and techniques. Okay, so now we'll see the exam corner, that is the weightage of marks was allotted by the state board. The number of hours will be 12. From a part A, that is 1 mark question, one question will be given from this chapter, and in part T, that is 5 mark question, 2 questions are present or given in the question number 35 and 36. 5 into 2, 10 plus 1, 11. Overall, 11 marks will be allotted for this chapter. And today we are going to discuss about the general introduction of organic chemistry, tetravalency of carbon and shapes of organic compounds, hybridization and bond characteristics, structure representation of organic compounds. These are the contents we are going to discuss in this session. Next, we'll see the introduction part of organic chemistry. Organic chemistry is a branch of chemistry which deals with the organic compounds or with the compounds of carbon. Whatever the compounds containing carbon and hydrogen more, we'll call it as organic compounds. Dealing of organic compounds, we'll call it as organic chemistry. It is nothing but a branch of chemistry. Apart from carbon, the major elements present in the organic compounds are hydrogen, oxygen, nitrogen, sulfur, phosphorus, chlorine, bromine, iodine are the minor elements present in the organic compounds. Whatever the compounds presence of carbon, will call it as organic compounds. With respect to or along with carbon, major compounds are hydrogen and oxygen. And there are so many heteroatoms called nitrogen, sulfur, phosphorus, chlorine, bromine, iodine are the minor elements present in organic compounds. In organic compounds, carbon atoms are bonded to one another and atoms of other elements by covalent compounds. We know carbon is bonded with another elements by covalent bond. Those compounds will call it as covalent compounds. And moreover, Berzelius proposed vital force theory, according to which a vital force is responsible for the formation of organic compounds. Berzelius was a scientist who told that organic compounds cannot be synthesized. It was synthesized or it was prepared before by the vital force. But this notion was rejected in 1828 when F. Hohler synthesized in an organic compound urea from an inorganic compound ammonium cyanate. Okay. In 1828, the notion or the what Berzelius statement was rejected by Hohler. When it was rejected, he proposed or he synthesized a organic compound, that is urea, from an inorganic compound called ammonium cyanate. This is the equation or the reaction. Ammonium cyanate gives rise to urea in presence of heat, and it was followed by the pioneering synthesis was acetic acid by Kolbe in 1845 and methane by Bartlett in 1856. First Hohler synthesized urea and he was followed by Kolbe and Bartlett. In coming years, that is acetic acid was synthesized by Kolbe and methane was synthesized by Bartlett. And it showed conclusively that organic compounds could be synthesized from inorganic sources in a laboratory. What Berzelius told, by a vital force, organic compounds are formed, we cannot synthesize. But through these scientists, it proved wrong, and they told Organic compounds could be synthesized by inorganic sources in a laboratory itself. And if we come to the carbon, we know that carbon is having two major properties. Those are catenation and tetravalency. First we will see what is catenation. Tendency of an element to form covalent bonds with identical atoms. Okay, it is a property of carbon. The tendency of forming covalent bonds with identical atoms, will call it as catenation. Ability of carbon atoms to link with each other to form long chain and closed chain molecules. Not only form catenation, the carbon is having the capacity to form a bonds with other elements as well. And non-metals with covalency of 2 or more show catenation. Carbon shows maximum catenation. Okay. Next, tetravalency of carbon and shapes of organic compounds. First we will see how the carbon is tetravalent and it forms 4 covalent bonds. That's why tetra means 4, valency. How the bonds will form? It is based on valency only. Tetra means 4. That's why carbon is forming 4 covalent bonds. That's why it is called tetravalent element. See here, shapes of carbon compounds. Electronic configuration of carbon is, this is atomic number of carbon is 6. In the ground state, 1s2, 2s2, 2p2. It's a general electronic configuration. When it has been excited, this 2p2 will become 2px1, 2py1, 2pz1, and here is also innermost electron, middle electron will jump here. So overall, all the excited state electrons will be followed. Due to the presence of 4 half-filled orbitals in a valence shell, carbon exhibits covalency of 4. Covalency is nothing but the capacity of forming bonds. How much in carbon? That is 4. That is forms a maximum of 4 covalent bonds in its compounds. If we tell carbon 1, 2, 3, 4. 4 bonds could be, covalent bonds could be formed with respect to carbon. That's why we will call it as tetravalent. How it is become tetravalent? By this electronic configuration. Next, hybridization and bond characters. What is that? First, we will understand what are the varieties of bond: single bond, double bond and triple bond. If we see the single bond, what is the hybridization? That is sp3. And number of bonds formed by the hybrid orbital is 4. And the geometry will become tetrahedral. In this sp hybrid orbital, s character will be 25. In the sp3 hybridization, p will be 75%. The cc bond length 154, ch bond length is 154, that is picometer. In double bond, it will form sp2, that is 3 bonds will form trigonal planar 33.3% and 66.7% of sp respectively, and 134 cc bond length in picometer, 110 in ch bond in, that is picometer. Triple bond sp, the number of bonds is 2, linear, here 50%, 120 in carbon-carbon bond length, 108 in carbon-hydrogen bond length. See here, sp3 means all are single bond, carbon-carbon, and this is carbon and hydrogen. All are single bond. This is first one what we have seen, carbon-carbon bond and carbon-hydrogen bond. Okay. If you want to see double bond, this is double bond, that is sp2, this is sp hybridization in triple bond. Okay, these are the kinds of bonds with respect to hybridization. Next is, from the table it can be concluded that sp hybrid orbitals have maximum s character, so it is closer to the nucleus and forms shorter and stronger bond. Yes, sp hybridization is close to nucleus and that's why it will form short and stronger bond. Okay, and the electronegativity of carbon atom is based on hybridization. What is electronegativity? Nothing but a pull of electrons towards the nucleus. pull off the shared pair of electrons toward the nucleus, we'll call it as electronegativity. It is based on hybridization. It is more in sp hybridization because sp is near to nucleus. It forms shorter and stronger bond. See here, order of electronegativity is sp more, sp2 and sp3 is least. That's what we told. This is near to nucleus, that's why electronegativity is more, and this is electronegativity is less. Electronegativity increases with increase in the percentage of S character of hybrid orbitals. What we will tell? Electronegativity is directly proportional to percentage of S character. When S character increases, obviously electronegativity will increases. This is directly proportional to one another. This is about the hybridization and bond characters. First we will see the characteristics of pi bond. A pi bond is formed by sideways overlapping of unhybridized p orbital of valence shell of electrons. See here, see this is ethene, right? This is all the elements are in same plane. How the p orbital will form? It is perpendicular to the carbon. This is p orbital. The pi bond is formed by sideways overlapping of unhybridized p orbital of valence shell of atoms. All the atoms attached to the carbon atoms in an electron system are lying in the same plane. This C, H, H, all the H and all the C are lying in the same plane. Only unhybridized p orbitals lie perpendicular to the plane of the molecule form a bond. This p orbital are perpendicular to the plane and it will form pi bond. Rotation of CH2 fragment with respect to the other interference with maximum overlap of p orbitals and therefore only restricted rotation about carbon-carbon double bond is possible. What will happen? This CH2 rotation is restricted, only the carbon-carbon double bond will move, but the restriction of CH2 will be forbidden because it cannot move due to the interference of overlapping. Presence of pi electron cloud above and below the plane of the bonding atoms makes pi electron easily available to the attacking reagent. That molecules with pi bond are more reactive than those of sigma bonds. What will happen? It is perpendicular, these p orbitals are perpendicular to plane. The attacking reagent, if it is comes to attack, automatically this p orbital will get attacked. That's why we will consider that pi bond electrons are more reactive than sigma bonds. These are the characteristics of pi bond. Once again, pi bond is formed by sideways overlapping and all the atoms attached to the carbon atoms in an electron system lie in the same plane. The p unhybridized orbital is perpendicular to the plane of the molecule. The rotation of CH2 fragment is restricted due to the interference or the overlapping, and the presence of electron cloud above and below the plane, it will be able to attacked by the attacking reagent, and that's why pi bond is more reactive than sigma bonds. Here indicate the type of hybridization of each atom in the following molecules. Okay, these are the three examples how you have to identify the each and compound. We'll see. Now first, this is in a condensed form. You have to elaborate. Right, this is the overall, and this is A, this is B, and this is C. See here, from A side and C side, it is forming double bond. That's why A and B will be sp2. Only C is having all the side single bond. That's why it will form sp3. Correct? See next example. All the side you have expanded form. This is A, B and C. This A and C will form sp2. Only B will form sp. Because it can be forming of triple bond. That's why A and C will form sp2. See here, double bond, double bond. In between B is formed sp. And if you want to discuss with the third example, C, B and this is A. Okay. See here, A is different, B is different and C is different. A is triple bond is there, that's why sp. B here once again sp because two sides double bond is present, and C is sp2 will form. See here, A triple bond is present, that's why sp. B two side double bond means once again sp will form. C is one side double bond, that's why sp2. This is how the indication of hybridization in the each atom of the following molecule. Okay. And indicate the number of bonds in the following molecules. There are two kinds of bond, that is sigma bond and pi bond. How you have to see the number of bonds with respect to sigma and pi bond means here also you have to elaborate the structure. Okay. All are having single bonds. That's why 1, 2, 3, 4, 5, 6, 7. Sigma 7 bonds, pi 0 bonds. And the second example, here also you have to expand the things. See here, if you are having a double bond, in that double bond, one bond will be pi and another bond will be sigma. That's why the number of sigma bonds is 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8 and pi bond is 1. Here also C see here, sigma 1, 2, 3, 4, 5. In this one sigma bond 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In the triple bond, two pi bonds will be there, one sigma bond will be there. Then in double bond, one pi bond, one sigma bond. Then how many pi bond? 3 pi bonds will be formed. You should remember, single bond means only sigma, double bond means 1 sigma, 1 pi, triple bond means 2 pi and 1 sigma will be present. If this is having a rule, if it is in your mind, you can indicate the number of sigma bonds and pi bonds easily. Okay. Next is structural representation of organic compounds. There are so many structural representation. We'll see one by one now. First one, complete or dash structure. In this, the two electron covalent bond is represented by a dash. A single dash represents single bond, double dash double bond and triple dash will form a triple bond. Okay. See here, this is a normal Lewis dot structure. These two electrons will form a bond. We know that. By that, this is a ethane, meth, eth. that rule you know. 2 carbon atom, that's why eth. All the single bond, ane, ethane. CH2 double bond, that's why ethene. And ethine, triple bond is there, we have written the structure. You have to remember single dash, single bond, double dash, double bond, triple dash means triple bond. It was based on the Lewis dot structure. In the condensed formula, when all the bonds except double bond and triple bond are omitted and the number of identical groups attached to an atom is represented by a subscript, the obtained structure is called condensed structure or condensed structural formula. Thus, ethane, ethene, ethine and methanol in their condensed form can be written as like this. How we will write the ethane? This is a expanded form. But what they have told? If you write all the expanded form as a subscript, it will understand how many atoms are present in between. Okay. Here also double bond. In between carbon and carbon, double bond will be present. Remaining 2 will be expanded. Here also triple bond will be present. Remaining 2 will be expanded. Like that you have to write. Similarly, CH3, CH2, 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 CH3 can be further condensed as CH3. First one, how many CH2s are present? 1, 2, 3, 4. See here, CH2 in bracket you have to write. Externally 4 and remaining CH3. This is a condensed formula. If you want to expand this, and you can write it in this form. Next is bond line structure. In this structure, the carbon-carbon bonds are represented by zigzag lines and terminal denotes methyl, that is CH3 groups, unless stated otherwise as a functional group. The line functions represent carbon atom bonded to appropriate number of hydrogen required to satisfy the valency of the carbon atoms. Example, bond line and condensed structure of 3-methyl octane are, see here, 1, 2, 3, 4, 5, 6, 7, 8. If it is 8 oct, right? And how many? All are single bond, that's why ane. In the third position, methyl group is attached, that's why 3-methyl, right? This is the normal form. But if you want to write it in a bond line, this is CH3, the terminal will be recognized or considered as CH3. This is at the middle CH2, 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 again this terminal will call it as CH3. Okay. Like this you have to write in a zigzag manner. But if it is present in oxygen, nitrogen with a functional group, you can write like this. The double bond O, or if it is present here chlorine, here bromine, or here bromine, like this. Anywhere you can attach the functional groups as well as triple bond also. If it is a double bond like this, triple bond like this, you can write it in a zigzag manner. This is a 3-dimensional representation of organic molecules. To represent an organic molecule in a 3-dimensionally, following convention should be kept in mind. What are those? Normal lines, solid wedge and dashed wedge. What does normal lines will show? It always shows the groups lying in the plane of the paper. If it is a plane, all the elements or the groups will be on the same plane. Solid wedge shows the bond projecting out the plane of the paper or towards the observer. Dashed wedge also shows the bond projecting out of the plane of the paper, but it is away from the observer. It is towards the observer, it is away from the observer. See here, the broad end of the wedge is towards the observer, keeping the observed conventions in mind. 3D structure of methane. This is methane structure. How they have written CH. This is solid wedge towards the observer. This is on the plane. this is far away from the observer. You can tell like this, solid wedge is above the plane also. Okay. Normal lines on the plane, this is what? Dashed wedge or lines is below the plane. Okay. These are the three ideologies of the three-dimensional representation of organic molecule. Write the bond line formula of each of the following. See here, how CH3, how many CH2? 1, 2, 3, 4, 5. Okay. CH3, CH2, 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 and this is CHO. Okay. How many? 1, 5, 6. Overall 7. 1, 2, 3, 4, 5, 6. Right. CH3, CH2, CH2, CH2. 1, 2, 3, 4, 5. You can write it in this manner. 1, 2, 3, 4, 5, 6. This is C. And this one, how many? 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5, 6. This is how the bond line representation can be written. And the condensed formula, how you will write? This is right. C, 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 carbon atoms all are present, and wherever double bond is present, you have to write CH, CH only. Wherever only single bond is present, there CH2. Okay. This is CH3 terminal, CH. Okay. Here also CH, double bond. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Here CH3, triple bond, CH. Here once again CH3, CH, CH. Once again CH. This is how the condensed formula will be written. See here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 with the double bond and triple bond representation. The remaining valency of hydrogen you should count and write. This is a cyclic manner and this is a acyclic manner. You will study about cyclic and acyclic in the classification of organic compounds. In the next session, you will study about classification of organic compounds, homologous series and nomenclature of organic compounds. I hope you have understood what I have taught today. So, we will meet in the next session. Thank you.